Good morning, everyone. Today I am going to present digital phase locked loop, commonly known as DPLL. This is an important concept in digital signal processing and modern communication systems. In this presentation, I will first explain why synchronization is necessary in communication systems. Then I will describe the basic structure of DPLL, including its main components such as phase detector, linear loop filter, and numerically controlled oscillator. By the end of this presentation, you will understand how DPLL helps in accurate phase and frequency synchronization in digital systems. Let us begin with motivation behind synchronization. Now let's understand why synchronization is necessary in digital communication systems. When a signal is transmitted, it usually modulated on a carrier wave. At the receiver side, we must generate a carrier signal that matches the frequency and phase of the transmitted signal. Only then we can correctly demodulate and recover the original information. However, in real world conditions, the received signal is affected by noise, Doppler shift, channel distortions, and oscillator mismatches. Because of this, the received signal may have a phase offset or frequency offset compared to the receiver's local oscillator. If synchronization is not achieved, the constellation diagram rotates in systems like QPSK or QAM, leading to incorrect symbol detection and an increase in bit error rate. To solve this problem, we use feedback system called digital phase locked loop, which continuously tracks and corrects phase and frequency errors. This is why synchronization is a fundamental requirement in modern communication systems. Now let us understand what a phase locked loop is. A feedback control system that locks the phase of its output signal to the phase of an input reference signal. It continuously compares phase of the incoming signal with phase of a local generated signal. Based on the phase difference, it generates an error signal. This error signal is used to adjust the oscillator. So that now let us compare analog PLL and digital PLL. An analog PLL operates in continuous time and is built in hardware components such as voltage oscillator, resistor, capacitors, and operational amplifiers. The oscillator frequency is controlled using an analog voltage. However, analog systems are sensitive to temperature changes, components, aging, and noise. On the other hand, a digital PLL operates in discrete time and is implemented using digital processor, FPGAs, microcontrollers, uh, instead of a voltage controlled oscillator, it uses numerically controlled oscillator or NCO. Instead of analog filters, it uses digital filters. The major disadvantage of digital PLLs is flexibility. Parameters like loop gain, bandwidth, filter coefficients modified through software without changing hardware. Because of their high stability, programmability, and precision, digital PLL preferred in modern digital communication systems. Now look at the basic block diagram of the digital locked loop consists of three main components: the phase detector, the loop filter, numerically controlled oscillator or NSO. First, the phase detector compares the phase of incoming signal with phase of the signal generated by NCO. It produces an error signal that represents the phase difference. Next, this error signal is passed through loop filter. The purpose of the loop filter is to remove high frequency noise and control the dynamic behavior of the system, such as stability and response speed. Then, The filter signal is used to control the NCO. The NCO adjusts its frequency and phase accordingly. Finally, the output of the NCO is fed back to the PEC, creates a closed loop system that continuously reduces the phase error until system locks. So overall, the DPLL works as a feedback system that automatically corrects phase differences. Now let us focus the first block of the DPLL, which is phase detector. The phase detector compares the phase of the incoming signal with the phase of the feedback signal generated by NCO. Its main function is to measure how much the two signals differ in phase. It generates an error that is proportional to the phase difference. If the phase difference is large, the error signal will be also large. If the signals are nearly synchronized, the error signal becomes very small. There are different types of phase detectors. Sinusoidal signals, a multiplier type detector is commonly used. For digital square waves, an XOR phase detector can be used. In more advanced systems, a phase frequency detector can be used. In more advanced systems, a phase frequency detector is used because it can detect both phase and frequency differences. The performance of the entire DPLL strongly depends on the accuracy and linear range of the phase detector because it directly influences how quickly and accurately loop locks. Uh, Looking at the mathematical representation of the phase error in a DPLL, the phase error is defined as the difference between the input phase and output phase. In simple terms, we can write it as input phase minus output phase. Phase error signal is the key quantity that drives the entire loop. It tells the system how much correction is needed. In reality, the phase detector output is often proportional to sign of the phase error. However, when the loop is close to locked condition, the phase difference becomes very small. We use small angle approximation where sine of theta is approximately equal to theta. This approximation simplifies the system and allows us to analyze it using linear control theory. So this mathematical representation is very important because it forms the basis of stability and analysis transfer function of modeling of the DPLL. Now let us move to the second important block of DPLL, which is loop filter. The output phase detector contains not only the useful phase error information but also high frequency components and noise. The loop filter is used to remove these unwanted components. It is mainly purpose is to smooth the error signal before it applied to NC. The loop filter also determines important system parameters such as bandwidth, damping factor, and response speed. If the bandwidth is too wide, the system may respond quickly but becomes sensitive to noise. If the bandwidth is too narrow, the system becomes more stable but slower to lock. Let us discuss the numerically controlled oscillator or the NSO, which is third main block of the DPLL. The NCO is responsible for generating the digital sinusoidal output. It replaces the voltage controlled oscillator used in analog PLL systems. The NCO works using phase accumulator at every clock cycle. A phase increment value is added to previous phase. This phase increment determines the output frequency. The accumulated phase is then converted into a sine or cosine value using a lookup table or a digital computation method. The important point is that the frequency of NCO is controlled by digitally by the filtered error signal coming from the loop filter. If there is a phase error, the NCO adjusts its frequency accordingly. The NCO is fully digital. It provides high frequency resolution precise control, and excellent stability. So the NCO acts as a adjustable oscillator that ultimately locks onto input. Understand the overall working principle of digital phase locked loop. The DPLL operates a closed loop feedback system. First, the phase detector compares the phase of the input with the phase of the NCO output. It generates an error signal based on the phase difference. Next, this error signal is passed through loop filter. The filter removes unwanted high frequency components and shapes the response of the system. Then the filtered signal is used to adjust the frequency of NCO. If the NCO frequency is lower than the input frequency, it increases. If it is higher, it decreases. This correction is process continuously, gradually the phase difference becomes smaller and smaller. When error phase approaches to zero and the output frequency matches the input frequency, the loop is said to be locked. At this point, the DPLL successfully tracks the input signal's phase frequency. Now let us discuss two important concepts in DPLL: capture range and lock range. The capture range is the range of input frequencies over the DPLL that initially acquire lock. In other words, if the frequency difference between the input signal and the MCO is within this range, the loop will eventually synchronize. The lock range, on the other hand, is the range of frequencies over which the loop can maintain synchronization once it already locked. Usually, the lock range is larger than the capture range. Therefore, proper selection of loop gain and filter parameters occurs that the capture and long range are suitable for intended application. Now let us look at the linear model representation of the DPLL. Although DPLL is inherently a nonlinear system due to sinusoidal relationship in the phase detector, analysis becomes easier when the loop is near the locker condition. When the phase error is small, we use small angle approximation where sine of theta is approximately equal to theta. This allows to represent the phase detector as simple gain block. In the linear model, phase detector is represented by gain constant, the loop filter by the transfer function. The NCO behaves like discrete time integrator. By using linear representation, we can derive the open loop and closed loop transfer functions of the system as follows. This linear model helps us analyze stability, transient response, and bandwidth of the DPLL system using control system techniques. Now moving to the stability of the digital phase locked loop. Stability is a very important factor because we want a loop to lock smoothly without oscillations or instability. In the linear model, stability depends mainly on the loop gain and the location of the poles of the closure transfer function. If the poles lie inside the unit circle in the Z domain, the system is stable. If the loop gain is too high, the system may respond very fast but can start oscillating or even become unstable. The system may respond very fast but can start oscillating or even become unstable. If the loop gain is too low, the system becomes very slow and takes more time to lock. The loop filter design also play a crucial role. Proper damping ensures that the system reaches the locked parameter, ensures fast, stable, and reliable synchronization. Now let us discuss the performance of the DPLL. Phase in practical communication systems, signals are always affected by noise. This noise introduces phase fluctuations, commonly referred to as phase noise. The DPLL helps reduce the effect of the phase noise by using loop filter. The DPLL reduces the effect of phase noise by using loop filter. The filter suppresses high frequency noise components in the error signal. However, there is a trade-off. If the bandwidth is wide, the system responds quickly to changes, but also allows more noise to pass through. If the bandwidth is narrow, the system rejects noise but becomes slower if the tracking frequency changes. So the design of the loop filter must balance between noise rejection and tracking speed. Proper noise performance ensures accurate synchronization uh, and reduces bit error rate in the communication. Now let us look at some important considerations in digital implementation of DPLL. Since DPLL is implemented in digital processor, FPGA or microcontroller, it operates using finite word length arithmetic. This introduces quantization effects. For example, the phase accumulator in the NCO has a limited resolution. If the resolution is low, frequency accuracy reduces. Higher resolution improves precision but increase hardware complexity. Another important factor is the sampling frequency. The sampling rate must be high enough to properly track the input signal without aliasing. Despite these limitations, digital implementation offers major advantages. It allows easy parameter tuning, stable operation, and integration with other processing blocks. Moving to applications of DPLL, one of the most important application is carrier recovery. In digital communication systems such as QPSK and QAM, the DPLL ensures that receiver matches the transmitted carrier in phase and frequency. DPLL is also used in frequency synthesis where precise and stable frequencies are generated digitally. In systems like GPS receivers, DPLL helps tracks the phase of weak satellite signals accurately. It also widely used in the software defined radio where most signal processing is implemented digitally. Because of its flexibility and accuracy, DPLL has become an essential component in modern communication and signal processing systems. Now, let us summarize the main advantages of the digital phase locked loop. One of the biggest advantages is high stability since it is implemented digitally, it has not affected by temperature variations or component aging like analog systems. DPLL also offers a high accuracy and fine frequency resolution, especially due to phase accumulator in the NCO. It provides better noise immunity because digital filtering techniques can be applied effectively. Finally, it is easy to integrate to modern digital platforms like DSP processors and FPGAs, making it suitable for advanced communication systems. Because of these advantages, DPLL is preferred over analog PPL in most modern applications. Finally, let us conclude the presentation. In this presentation, we discussed the concept of digital phase locked loop and why synchronization is essential in the digital communication systems. We examined the basic structure of DPLL, including phase detector, loop filter, and numerically controlled oscillator. We understand how these blocks work together in a closed loop systems, how these blocks work together in closed loop systems to reduce phase error and achieve synchronization. We also discuss mathematical modeling, stability considerations, noise performance, and practical implementation aspects. Overall, the DPLL combines principles of control systems and digital signal processing to achieve accurate phase and frequency tracking. Due to this stability, flexibility, and digital implementation advantages, DPLL plays a crucial role in modern communication systems such as carrier recovery, clock recovery, and software defined radio. Thank you for the attention.